Alright, we are in 15.7, which is triple integration. Example 3 says evaluate the triple integral of the root of x squared plus z squared for the solid bounded by the paraboloid y equals x squared plus z squared and the plane y equals 4. Alright, we have a lot going on here. So first of all, note that we are given this function here that could be in terms of x, y, and z or whatever, but we're trying to evaluate this integral. And our domain space now is in 3D. And so we have that acknowledged with our triple integral, it's E and it's dV here. And that's described as a solid bounded by the paraboloid y equals x squared plus z squared and the plane y equals 4. So a lot of these problems is just trying to understand that 3D bounded solid and then set up the triple integral from that. We are not even going to approach graphing the inside of this triple integral, the root of x squared plus z squared. That's just kind of like in the background of something that we're going to have as our function to integrate. And so that's an adjustment here, that what we're trying to graph here, or sketch E, or think about it, is just our domain, which used to be just in 2D space, and now it's in 3D space. Okay, now that we get that taken care of, we're going to start thinking about it. So the paraboloid, when you have no square with the y here, that's like y is a function of the other two things. And you can see that, for example, that cross section, looking at a fixed y, is going to be a circle, and that when x and z are 0, y is going to be 0, so that's this place where we have sort of the parabola in the, if we're looking at the YZ plane, for example. And then we have a circle in the XZ plane. So you could plot a few XZ pairs to kind of see what's going on, or think of the cross section there, and this is what this thing looks like in 3D. And then also note that y equals 4, that plane is cutting it off on the top. So the main thing here is we're trying to describe E with bounds of the integral. First of all, this domain here in 3D space is not a box, which means that it's not just going to be just little numbers for all three integrals. We're going to have at least one set of variable bounds. So we're going to try to figure that out right now. And you can see that the way that the function is written for the domain, y equals x squared plus z squared, so that's part of the picture here, that y is a function of x and z. So pretty much the way that this is probably going to be the best to set up is to first integrate with respect to y. So if you start trying to set up the variable bounds in terms of like our y, and then have some bounds on it, note that we're looking at this now in 3D space, and what's like the least surface in terms of y, or y in terms of something, in this case x and z. So in other words, for y getting bigger, this is a y-axis here, then the least y is over here, and then it's moving to bigger y as we move to the right in the screen. So then, looking at the screen here, the surface that is defining the least y is that paraboloid, y equals x squared plus z squared, so that is the lower bound for y. And then there's a plane y equals 4 that is the greatest y. So there are variable bounds, well, not the 4, but we got that surface of the paraboloid taken care of in one of our bounds. And that's going to be our innermost one. Alright, trying to scroll here. So in a previous part of this notes, we talked about type 1, type 2, and type 3, not to memorize that or anything, but just to kind of give an introduction on what you could expect. And so the important point here is that I want to start setting up the bounds on my integral, and the one variable that's going to go first is y, and then I can write in the bounds in terms of y. So it's not necessary to Actually, what kind of works out well in some of these is to not even necessarily try to go all the way through and write in your bounds for the other double outer integrals. But, I mean, you do need to kind of think about it and make sure that this is all going to pan out. So, right now, we're going with this innermost integration. In terms of y, we got our bounds all figured out. So what would that leave behind? Well, kind of like with double integrals going down to a single integral from Calc 1, what we're accomplishing here is once we take care of the innermost integrals in the triple integral, then the outer one is just a regular old, super old, not quite actually super old, but in the recent history, a double integral. And that's all it's going to be. So that is going to be over the domain D. And for this particular problem, because we're integrating with respect to y first, then our other two integrations have to be in terms of x and z. So if we were going to look at the domain in terms of x and z, then that's going to be the circle here that's projected down to the xz plane, or you can think of it as being like the widest part of our domain E, this 3D solid that projects down on the xz plane. Alright, so here's an illustration with, in green, the domain D. And then maybe you start trying to look at that and say, okay, that's going to be when y equals 4, so I can set that equal to my paraboloid with the y being equal to 4, and that's the circle with radius 2. So then you can maybe start plugging that in to your double outer integrals, but then noting, okay, actually this would be easier to do in polar. So this is kind of a lot to wrap your head around. But one of the nice things about these triple integrals, and I kind of alluded to this, is why don't you just do that innermost integral? You can do that right now. And then it's going to boil down to just a regular old double integral. And you know how to do double integrals with polar. So then you can just address that at that time. So in other words, it's not necessary to switch this whole entire problem into trying to do something with polar, actually, that you don't want to do that. So now that we kind of thought about our domain D, let's actually just do the inside innermost of the triple with respect to y. Okay, so that's really easy to do. We've been kind of talking about it a lot, but we have x and z here, which we can hold fixed, and the integral with respect to y just attaches on a times y with that. Then you need to plug in. So we're going to do our 4 first, and then our x squared plus z squared in there with the minus parentheses. And so that was just evaluating that innermost integral with respect to y. And now you can see, hey, this is just a double integral over domain D, which is over the xz plane. Now you can start switching over to polar, and you're maybe a little bit more motivated here because you have all sorts of junk that is x squared plus z squared, and that's more easily represented as r squared. So you can go ahead and start addressing the integrand here, which is the function on the inside of the integral. Do some of that. Reminder that dA is equal to r dr d theta, or d theta dr. So you can get that squared away. We're also going to have to plug in for our domain in terms of polar, which the big motivator here is this is the polar rectangle because it's centered on at the origin in terms of xz, and then we can just define that whole space with a radius going from 0 to 2 and sweeping through the whole entire 360 degrees at 0 to 2 pi. So this is a polar rectangle. I can just use non-variable bounds if I do in polar. So we get this set up here. Different ways to do this integration. D theta, you could set this up in terms of two integrals and do the d theta 1 times the 1 in terms of r. Here I just decided to keep it all together and just do the d theta first. The integral of something with respect to r is going to, being held fixed, is just going to be times theta when we integrate. And I'm doing that term by term, so I get two thetas. And then I plug in my 2 pi and my 0 with a minus between. Simplify. And then we can go ahead and easily integrate with respect to r, just using the power rule. And then we're going to plug in. And finally simplify, and we get 76 pi over 5. So this is a challenging problem at first, a lot to think about. This is going to be something that we're actually going to do in the next section as well. So absolutely necessary to really try to get this down eventually.